Today we're going to be talking about exponent properties because these are very important at every single level of math that you look at, and in the immediate future it's going to be very important to be able to manipulate polynomials to do anything more complicated than add and subtract. So let's rederive why some of the exponent properties work the way they do. So in particular, all of this derivation is going to come from the fact that we know that if we say 2 to the 4th power, that means that we're multiplying that base of 2 times itself 4 times. So in this case, what you always want to read is that the base tells you what is being multiplied times itself, and then the exponent, why am I using the same color? The exponent tells you how many times to multiply. So let's derive some of these. So in particular, for the product property, that's getting at this fact that what if I have x to the m times x to the n? Well, let's rederive it with something a little bit more concrete. What if I had written 2 to the 4th times 2 to the 2nd? Well, that literally means 2 times 2 times 2 times 2 times another 2 times 2, because I have 4 2's times 2 more 2's. Or how could I more succinctly write that? 2 to the 6th power. What did I do with those two exponents? Well, ultimately I added them to give us 2 to the 6th. So in general, if I have the same base to an exponent times the same base to another exponent, what I'm going to end up doing is adding those exponents. For the power property, that's getting at the idea of what if I have an exponent of an exponent? Well, we can rederive that as well. If, for example, I had 2 to the 4th squared, keep in mind that means I've got 2 copies of 4 2's being multiplied by themselves, or more succinctly, that would be 2 to the 8th power, which would have come from doing 4 times 2. So in general, what you do is you then multiply the two exponents together if you have an exponent of an exponent. For the quotient property, quotient meaning division, that's getting at the idea of, well, what if I have x to the m divided by x to the n? Well, we can rederive that with something like, what if I have 2 to the 5th divided by 2 to the 3rd? That would be, let me also write that 2 to the 3rd a lot neater. That would be that I have 5 2's divided by 3 2's, and 2 divided by 2 makes 1, 2 divided by 2 makes 1, 2 divided by 2 makes 1. I would be left with 2 squared. In this case, what did I just end up doing with those exponents? I subtracted them. And that's in general how the quotient property works, is you are going to subtract those two exponents. We can use that property to derive the zero exponent property, because if, for example, I had 2 to the 5th divided by 2 to the 5th, the quotient property tells me that that should be 2 to the 5th minus 5, aka 2 to the 0. And I know anything divided by itself is 1, so 2 to the 0 better be 1. So in general, regardless of the base, if I have anything to the 0th power, that's going to get me 1. Very similarly, we can also use that quotient property to derive what happens with negative exponents. Because if, for example, let's change it to yet another color here. If I had 2 to the 3rd divided by 2 to the 5th, a similar sort of deal is going to happen as what I saw last time, but instead we have divide by 1, divides into 1, divides into 1. I would be left with 1 over 2 times 2, aka 1 over 2 squared. And by the quotient property, 2 to the 3rd over 2 to the 5th should have given me 2 to the negative 2nd, since 3 minus 5 is negative 2. And 2 to the negative 2nd I know is now equal to 1 over 2 to the 2nd. And so the generic way of saying that is if I have x to the negative n, that's the same thing as 1 over x to the n. So I can always flip where he is on the fraction or write its reciprocal and then take it to that positive version of the power. If I have a product or quotient with the power property, if I had something like x over y to the n, that would be the same thing as x to the n over y to the n, and similarly xy to the n is equal to x to the n y to the n. So we're distributing that out. Why does that work? Well, if I had 2x to the third, that's the same thing as 2x times 2x times 2x, which I could rewrite as 2 times 2 times 2 times x times x times x by the commutative property of multiplication, which is the same thing as 2 to the third times x to the third. So I effectively distributed that exponent to both terms. That is also allowed. And that is what this is saying in symbols. So you can sit there and memorize the rules if you want, or you can think through why do they work the way they do. So with that in mind, let's go ahead and practice simplifying some of these. So I know there's quite a few of these, but I would actually still encourage you to go ahead and pause your video and try to simplify all of these without the use of a calculator, where they all turn out to have only positive exponents. So let's go ahead and do some simplification. If I have negative 3 to the second power, keep in mind that means negative 3 times negative 3. That's going to become positive 9, since a negative times a negative is a positive. Versus if I don't have those parentheses, technically this negative 2 squared means negative 1 times 2 squared, because there was no parentheses there. 2 squared is going to get us 4, because it means 2 times 2. Negative 1 times 4 gives us negative 4. Versus if I have negative 2 all squared, keep in mind that's negative 2 times itself, and a negative times a negative is a positive. If I have a fraction all being taken to the same exponent, keep in mind that's the same thing as negative 1 to the fourth over 3 to the fourth. Negative 1 to the fourth means I'm doing a negative times a negative times a negative times a negative, which will end up giving me a positive. 1 times 1 times 1 times 1 ends up still just equaling 1. 3 to the fourth, well, 3 squared is 3 times 3, which is 9, times another 3 is 27, and then 27 times yet another 3. 3 times 7 is 21, carry the 2. 3 times 2 is 6, plus 2 is going to give us 8. So this will simplify to 1 over 81. And again, be very, very careful about the placement of parentheses here. For this next one, that negative's on the outside, so keep that in mind. That's negative 1 times 4 squared over 9. Then 4 squared, that means 4 times 4, that's going to get you 16. Negative 1 times 16 gets us negative 16, and negative 16 over 9 is as simplified as it gets. Again, be very, very careful about placement of parentheses on this next one. That's really negative 1 times 3 to the negative third. 3 to the negative third, whenever I have a negative exponent, that becomes 1 over 3 to the positive third. So you're going to flip the fraction, and then you're also going to flip the sign on that exponent. Then 3 to the third is 3 times 3 is 9, times another 3 is 27. So this becomes negative 1 over 27 as a final answer. Now we're getting into ones that also involve variables, but those rules are still the same. So if I have 5xy all to the third, that means I have 3 copies of 5 being multiplied by itself, 3 copies of x is being multiplied by itself, and 3 copies of y being multiplied by itself. For the 5 to the third, 5 times 5 is 25, times yet another 5 will give me 125, times x to the third, y to the third. For this next one, I find it helpful to go ahead and rewrite everything as a positive fraction first. So x to the negative 4 becomes 1 over x to the fourth, being multiplied by 1 over x to the sixth, since that x to the sixth does not move because he is a positive exponent. X to the fourth times x to the sixth, that's 4 x's times 6 more x's, will become x to the 10th. For this next one, I like to do the same thing of, first I'm going to distribute that negative to both terms. So I have x to the negative 7 over y to the negative 7. And then for the negative exponents, that's going to flip the location on the fraction. So it becomes y to the positive 7th over x to the positive 7th as our final answer from that negative exponent, again meaning that it's the reciprocal to the positive exponent. This next one, I would encourage you to go ahead and get rid of those negative exponents first. That becomes x to the 3rd times x to the 4th over now x to the positive 7th, because that negative 7 moves him to the denominator. X to the 3rd times x to the 4th becomes x to the 7th, because there's 7 total x's being multiplied by itself. And then anything divided by itself is just going to become 1. For this next one, it doesn't really matter what's going on in the middle there, because this is all being taken to the 0th power, and anything to the 0th power is 1. For this next one, there's a couple different ways to go about it. If I were still to just sort of systematically do the exponent of an exponent. Exponent of an exponent means that multiplies by itself, so negative 6 times negative 2 is going to get me a positive 12. That would be one way of approaching it. If you kind of wanted to step by step get rid of the negatives, you would still find the same thing. Because for the inside, y to the negative 6 becomes 1 over y to the positive 6th. And then to the negative 2 is going to flip that fraction again, so that becomes y to the positive 6th to the positive 2nd, and then 6 times 2 still gets us 12. So regardless if you sort of do all of the flipping of the fractions first because of that negative, or if you go ahead and just jump to doing the exponent of an exponent, means I multiply them together. Either way, you're still going to get the right answer. For these more complicated ones, I would definitely deal with those negative exponents first before tackling much of anything else. So in particular, for this first one, I'm going to go ahead and just anybody who's a negative, I'm going to flip his location on the fraction. So that becomes 2 to the positive 4th over 2 to the positive 8th, x to the positive 5th over x to the positive 2nd, and then the y to the 3rd and y to the 6th don't have positive exponents, negative exponents. They're still positive, so they're just going to stay where they are. Then I'm going to go ahead and do those division of the like bases. So 2 to the 4th over 2 to the 8th leaves us with 2 to the 4th in the denominator, because the denominator is bigger. X to the 5th over x to the 2nd is going to leave us with x to the 3rd in the numerator, because that numerator is bigger. Y to the 3rd over y to the 6th is going to leave us with y to the 3rd in the denominator, because that denominator is bigger. And again, you could think of that with that formal subtraction. So 4 minus 8 gives us negative 4, the negative meaning it ends in the denominator. 5 minus 2 gives us positive 3, the positive 3 means he ends in the numerator. 3 minus 6 gets us negative 3, the negative means he ends up in the denominator. Or you could also formally expand it out, so we would have had 4 2's times 5x's times 3y's over 1, 2, 3, 4, 5, 6, 7, 8 2's times 2x's times 6y's. That could be another way to do it, and then you're going to see what cancels and what's left. 2 divided by 2, 2 divided by 2, 2 divided by 2. Oh my gosh, I'm left with 4 2's on the denominator. Similarly, x divided by x, x divided by x, 3x is left in the numerator. Similarly, y divided by y, y divided by y, y divided by y, 3y's left in the denominator. So for the next two, I would encourage you to go ahead and try that yourself, and then we'll go over it together. So for the next two, I'm going to go ahead and personally simplify inside the parentheses, and I'll deal with that negative 3 on the outside. For simplifying inside the parentheses, first I'm going to deal with all these negatives. So anybody who doesn't have a negative exponent, I'm going to leave where he is. If he does have a negative exponent, I'm going to flip his location. So that x to the negative 3 ends up on the bottom, that other x just stays as is. That both of these y to the negative 2's basically end up switching locations. So the one on the bottom goes to the top and becomes positive y squared. The one on the top goes to the bottom, becomes positive y squared. That z to the 4th stays on top, and then that z to the negative 4 on the bottom goes to the top. Then I'm going to go ahead and start to simplify the inside a little bit before dealing with that outside exponent. So 12 divided by 3 is 4. Y to the 2nd divided by y to the 2nd just makes 1. X to the 3rd times x makes x to the 4th on the denominator. Z to the fourth times Z to the fourth makes Z to the eighth in the numerator, all being taken to the negative 3. The negative part means everybody is going to flip their locations, so I'm going to go ahead and do that first. So that becomes x to the fourth over 4 z to the eighth all to the positive third. And now I'm ready to go ahead and distribute that to the third power to each term. So x to the fourth to the third power means I have a total of 12x's multiplied by itself. 4 to the third becomes 4 times 4 is 16 times another 4 is 64. Z to the eighth to the third means I have a total of 24 z's being multiplied by each other, and that would be my final answer. For the last one, again, I'm going to deal with those negatives first. So that negative 3, be careful, he's not being taken to a negative exponent. He actually stays location-wise where he is. Then we have an x to the fifth over y to the negative 6 will become a y to the positive sixth in the denominator. Times, similarly, this positive 5 is not being taken to a negative exponent, so he stays as is. The x to the negative 1 moves to the denominator. He's being secretly taken to the positive 1, but I would tend not to write that. And then we have y. Now we're going to go ahead and start multiplying our like terms. So negative 3 times positive 5 gives us negative 15. X to the fifth divided by x leaves us with x to the fourth on the numerator. And then divided by y to the sixth leaves us with y to the fifth in the denominator. And that would be our final one. And again, there's multiple ways to approach these, but as you saw, I would recommend sort of getting rid of those negatives and flipping the locations of the guys as quick as possible. But be careful that a negative attached to the actual number is not the same thing as a negative inside the exponent. Negative in the exponent tells you location. Negative on the actual number on the base just tells you the value of that number.